Hey everyone, ever wondered how future videos will look when you can step inside them? Imagine watching a 3D video where you can look around freely, like you're really there. That's the promise of volumetric video, but there's a big problem. Traditional methods either look flat or are too slow to stream. Today, we're diving into a groundbreaking new approach called adaptive 3D Gaussian Splatting that's changing the game. Let's start with the basics. Volumetric video isn't just 3D, it's a full interactive 3D world. Think of it like a digital clone of a real scene, where you can move your head and see every detail. But here's the catch, these videos are massive. A single frame can be 49 megabytes. For a 30 FPS video, that's 11.76 gigabits per second, way too much for your internet to handle. Enter 3D Gaussian Splatting, 3DGS. This tech uses hundreds of thousands of tiny, adjustable Gaussian shapes, like 3D paint splats, to build scenes. Each splat holds info about color, size, and direction, letting creators make super realistic, editable 3D worlds. It's way better than older methods like point clouds or meshes, which struggle with details and lighting. But here's the kicker, 3DGS videos are even harder to stream than traditional ones. Why? 3 main reasons. 1. Size, each frame is huge, like a 49 MB photo. 2. Saliency, not all parts of a scene matter equally. Your eyes focus on certain areas, but 3DGS's random splats make it hard to know what's important. 3. Compression, unlike uniform points in a cloud, each 3DGS splat is unique. You can't just toss out the less important ones without ruining the image. So how do you stream something so data-heavy? The researchers behind this study came up with a smart solution. They split the video into adaptive tiles, like puzzle pieces, that change based on what's visually important. Think of it as a spotlight. The most interesting parts stay sharp while the rest gets compressed. They also use differentiated quality modeling, which means some areas get higher quality than others, like a high-res foreground and lower-res background. Here's the magic. By analyzing saliency, what your eyes are drawn to, and using hybrid tiling, the system adapts in real time to your internet speed and where you're looking. If you're watching on a phone, it sends you the most critical details. If you're on a VR headset, it prioritizes the parts of the scene you're facing. The results? Their method outperforms existing techniques in speed, quality, and efficiency. It's like upgrading from a dial-up connection to fiber optic, smooth, immersive, and ready for the future of 3D content. But let's dig deeper. Traditional 3D Gaussian Splatting, 3DGS, stores all Gaussian points for every frame, creating massive redundancy. It's like saving a whole library of books for each page of a story. This leads to bloated files and inefficiency. Plus, when scenes move, like a person walking or a car driving, the models can drift or become inconsistent. It's like watching a video where the characters glitch out. To fix this, researchers developed dynamic 3DGS, which evolves over time. But even this has challenges. Capturing long-term motion without errors. That's tough. And complex movements, like a crowd or a storm, can break the models. Their solution? Breaking videos into shorter segments called GoFS, groups of frames. Think of each GoF as a mini video. Within each, they create a deformation field, a map showing how points move over time. Because each GoF is short, motion is simpler to track, avoiding the chaos of long sequences. They also separated foreground, like a person or object in focus, from background. Why? Most motion happens in the foreground. By focusing on that, they reduce model complexity. It's like zooming in on the action while keeping the scenery simple. To make this work, they used a dynamic neural network that learns which parts of the scene are important. Then they applied adaptive tiling, dividing the video into chunks based on visual interest. High-interest areas get more detail, while less important parts use lower quality. It's like prioritizing the plot of a movie over the background scenery. In tests, this method outperformed existing techniques. Sharper images, smoother motion, and way less data needed for streaming. By intelligently choosing which parts of the video to send, they deliver high-quality 3D experiences even on slow internet. But here's the real kicker, how they handle data transmission. Think of it like sending a package. If you split it into tiny pieces, like 64 tiny tiles, it's fast but can get jumpy. If you send big chunks, no tiling, you might waste bandwidth. Their adaptive tiling system. It's the Goldilocks solution, just the right size. In lab tests, under both stable and super shaky 5G networks, their method used less data while keeping quality high. Even when internet speed went haywire, the system adjusted on the fly, avoiding lag or pixelation. It's like having a GPS that reroutes you when there's a traffic jam, only for video data. And here's the tech magic, rendering 3D videos in real time. On a desktop, it's 246 frames per second, faster than your eyes can blink. On a VR headset, 126 FPS. That's smooth enough to spin around and still see every detail. But even that isn't enough for super complex scenes. So they added a dual-mode transmission. Think of it as having 2 delivery trucks. One sends pre-built tiles for speed, the other handles dynamic adjustments. The results? PSNR, SSIM, and LPIPS, 3 metrics that measure video quality, showed their method outperformed the competition. Lower LPIPS means the video looks more natural to your eyes, while higher PSNR and SSIM mean less distortion. It's like upgrading from a blurry old TV to a crystal clear 4K screen. This isn't just about better videos, it's about making 3D content practical for real-world use. From virtual reality to remote collaboration, this tech could change how we interact with digital worlds. So next time you watch a 3D video, remember, behind the scenes, there's a whole lot of smart math making it possible. Thanks for watching. If you want to dive deeper into how this works, check the links below. And don't forget to like and subscribe for more deep dives into the science behind your favorite tech. Imagine you're watching a 3D video of a bustling cityscape. Every detail, every shadow, every flicker of light. Now imagine that same video using way less data while still looking stunning. That's the breakthrough we're talking about today. Let's start with the problem. Traditional video compression methods struggle with 3D content. They either use too much data or lose critical details. But our new approach, it's like giving your video a superpower, clearer structures, sharper details, and fewer annoying glitches. We tested it against the best existing methods, and the results. Mind-blowing. Take PSNR, SSIM, and LPIPS, three fancy metrics that measure video quality. Our method outperformed the competition across the board. Lower LPIPS means the video looks more natural to your eyes, while higher PSNR and SSIM mean less distortion. It's like upgrading from a blurry old TV to a crystal clear 4K screen. But here's the real kicker, how we handle data transmission. Think of it like sending a package. If you split it into tiny pieces, like 64 tiny tiles, it's fast but can get jumpy. If you send big chunks, no tiling, you might waste bandwidth. Our adaptive tiling system. It's the Goldilocks solution, just the right size. In lab tests, under both stable and super shaky 5G networks, our method used less data while keeping the quality high. Even when the internet speed went haywire, our system adjusted on the fly, avoiding lag or pixelation. It's like having a GPS that reroutes you when there's a traffic jam, only for video data. And here's the tech magic, rendering 3D videos in real time. On a desktop, it's 246 frames per second, faster than your eyes can blink. On a VR headset, 126 FPS. That's smooth enough for you to spin around and still see every detail. But even that isn't enough for super complex scenes. So we added a dual-mode transmission. Think of it as having two delivery trucks. One sends pre-built tiles for speed, the other handles dynamic adjustments. This is just the beginning. As 3D content becomes more mainstream, innovations like adaptive 3D Gaussian Splatting will make immersive experiences accessible to everyone. Stay tuned for more deep dives into the future of AI and 3D technology.